Now let's get back to classification. Recall the classification framework in which we have a training data, which is a set of examples, each example described by a set of features, and the label Y. Label Y is categorical or qualitative. It belongs to a set Y, which would be, in the case of classification, we like to use labels like -1, +1, or 0, 1. The goal of classification is to learn a classification function f that maps the features to the labels in Y. We talk about linear classification when a classification model is said to be linear if it is represented by a linear function or linear hyperplane. Examples of classification include our toy example of bananas versus oranges, classifying email between spam and ham, classifying benign from malignant tumors if we have images of for breast cancer. Also, in the case of helping a bank to decide what kind of to whom to give a credit, we could classify credit default versus non-default to identify which customers will default on their credit card. In which case, we would have a data set of customers described by their features, along with a label that tells whether which customers defaulted versus those who didn't default. Plotting this data in 2 dimensions will lead to this figure in which we have the balance and income that are the 2 features. We put the labels as a plus or a circle here that tells which customers defaulted, which customers did not default. And building a classification here means to find the decision boundary that separates the pluses from the circles. Let's now talk about the perceptron algorithm, which belongs to neural networks, the class of algorithms that try to mimic how the brain functions. The first algorithm used was called the perceptron, invented by Rosenblatt in 1959. It actually, in general, neural networks work extremely well to recognize handwritten characters, spoken words, and faces. The method was very popular in the 90s, but then lost some of its popularity. But it's now back with the rise of deep learning. Typically, the perceptron algorithm works when we want to separate perfectly separable data, just like in this case. We have the plus examples well behaved on one side, and we have the minuses on the other side, in which case we could identify one of the linear functions that separates these 2 classes. So the perceptron algorithm is a linear classification method. It's one of the simplest one, actually, and it represents the simplest neural network out there. It works only then on perfectly separable data. As I said before, inspired by biology, the perceptron mimics the simplest functioning of our neurons at the single neuron level. Each neuron takes as input a set of real values and output one single value. This can be the input to other neurons. The perceptron specifically has as input the set of features from the data, so these are the feature values, and performs the linear combinations of those values. Then the output is going through a step functions in which the output is 1 if the linear combination exceeds some threshold, -1 otherwise. So we could write typically that the function that we want to learn, or the model, is the sign of a weighted sum of the feature values. Again, the perceptron algorithm works perfectly if the data is linearly separable. This is a condition for it to converge. If not, the algorithm will simply not converge. The idea of the perceptron is to start with a random hyperplane and adjust its weight using the training data. So you're going to feed the data into the perceptron, and whenever you make mistakes, you're going to revise those weights. So it's an iterative method that would go through the examples and try to fix and to match actually the input values to the output by changing the weights accordingly. So the algorithm is as follows. So the input, we have, as usual, our set of feature values along with the label. And the output is the hyperplane. So since we are talking about linear classification, we're going to obtain the weights of the hyperplane. The weights would be are called typically in perceptron W's. In linear regression, we were talking about the betas. But so the weights would be, we have in 1 weight per dimension or per feature. So we will have W1 through WD plus W0, which represent the offset or the intercept. So the algorithm starts by initializing the weights to 0. So the weights of all the features will be set to 0. And it will repeat until convergence. Repeat what? Check for each example how the current model or how the current weights that define the hyperplane are doing on each example. So we're going to go through all the examples, and for each example, we check whether the current model, the current weight, are classifying or misclassifying the example. For this purpose, what we can do is to simply multiply the true label yi by the function of this example, which means that we apply the model, the current weight, to the example and see whether we are making an error or not. So if it happens that the product of yi times f of xi is negative, means that we have two labels of different polarity, which means that we are getting an error. If it's an error, then we're going to adjust the weights. The current hyperplane does not classify this example that we are trying to test. All right, so after this, if we make a mistake, what will happen is that we're going to fix this hyperplane. It's not a good one. It's misclassifying this point. The way to update the weights is to just take the old weights and adjust them by adding yi times xi. So yi is the true label, xi is the feature value itself. So the process will repeat itself until convergence, which means that we're going to find one hyperplane or one line separating the data, the positive from the negative examples. Here are some observations about the perceptron algorithm. So first of all, the weights W1 through WD determine the slope of the decision boundary, right? So this determines what kind of hyperplane we are getting. W0 determines the offset, or we call it also percept in the case of regression, determines the offset of the decision boundary. Sometimes in the literature we find it noted as a B. Let's clarify what line 6 represents. Line 6 represents updating the weights. How do we update the weights? If we make a mistake on a positive example, which means that yi is +1, f of xi is -1, then the way to fix the weight is to add x to the weight vector, right? So I'm going to tilt the hyperplane accordingly. If we make a mistake on a negative example, we're going to subtract x, so as we cover properly the example that we have. Mistake on negative means that the example is -1, but we predict it as +1 with the current weight. So I have to update the weight accordingly. So we subtract x from the weight vector. There are some other variants of adding or subtracting x from the weight vector, and one of the variants is to add or subtract 1, which is just provides a different speeds of convergence, but it's the same principle. Convergence happens when? It happens when the weights do not change anymore. So we reached out a hyperplane that actually perfectly separates the positive from the negative examples, and there is no need to update the weights anymore, which means that in our condition here, yi f of xi never becomes negative anymore for all the data points. Here's a toy example illustrating the principle of the perceptron on a few data points. So we have two classes. The red points represent the positive class, and the blue points, let's say, represent the negative class. So we start initially with a random hyperplane that actually misclassifies most of the data. So this hyperplane we have, if we think that everything on the top is red, everything on the bottom is blue, then it is misclassifying this blue, 4 blue points here. By changing the hyperplane, we are just moving the line back and forth until this line classifies the data properly. So this is the progression of the line. At some point there will be some convergence, and the line will actually be able to classify the data perfectly, just like in this configuration. So finally, convergence. Each single data point is classified properly. Anything that is up from the hyperplane will be classified as red. Everything on the bottom will be classified as blue. So we could plug in this data some examples, some test examples, and see whether we are doing well. So if we have additional data points, you would see that we would classify them as positive if they are on the top of the hyperplane, or negative if they are on the bottom of the hyperplane. Note that the W's determine the contribution of each of the features to the label. So you do a linear combinations of those W's times the features x to see how this actually affects the label. Note also that minus W0 is the quantity that the weighted sum, right, of the features needs to exceed in order for the perceptron to output 1. Finally, the perceptron can represent any Boolean functions, such as the and, the or, the not and, the not or, and the not negation, but cannot represent others. For example, consider the or function, for which we have typically examples lying in positive examples on on this side and the negative example on the other side, in which case you have, if you have 0, 0, the output of the OR function is 0, but anything else in which we have at least 1, 1 would have an output of 1. However, for the XOR, we would have data points that lay on, so we have the positive points on this side, the negative points on this side, and no matter how we try to draw this separating hyperplane, it's not possible to find anything that would separate perfectly our data. So in this case, the XOR is not a Boolean function for which we could build the perceptron. Okay, so the idea of neural networks is actually to use many perceptrons to build a neural network. So network use the ability of single perceptron to represent elementary functions and combine them in a network of layers of elementary questions. However, a cascade of linear function is still linear, and we want networks that represent highly nonlinear functions. So we'll see this in the next lecture. A final observation here is that actually the perceptron picks one hyperplane or one line separating the data. There are actually many other lines that could be good candidates, so which one is the best? There are lots of possible solutions, and the idea of methods like support vector machines is to find this optimal solution rather than just picking one of the possible solutions. In the next lecture, we are going to talk about neural networks, which is combining a set of perceptron in order to solve more complex problems.